Hi, everybody, and welcome to our virtual WEF Student Design Competition presentation. My name is Eric Costello, and I'm the project manager for the National City Paradise Creek Flood Mitigation Project. Working with me, I had Marina Balcazar, Sophia George, Michelle Melkonians, and Julia Moore. So over the next 20 minutes, we'll take you on a ride through the wacky world of stormwater in National City. Specifically, we're going to focus on some of the seasonal flooding issues that they're experiencing. You can see on this slide kind of the layout that our presentation is going to take. And without any further ado, I'll turn it over to Michelle to give you some background on the project.
So first, for the background, we're going to look into the project Vicinity. Now, Paradise Creek is a tidally influenced creek located in National City, a city just south of San Diego, California, shown in the left figure. And the right figure shows our area of interest in relation to the iThe culverts and Kimball Park. Now we're going to tell you about the issue of Paradise Creek. Now, San Diego County experiences seasonal king tides between the months of December and February. These tides can rise to more than 9 feet above sea level, which causes significant flooding problems for low-lying areas such as Paradise Creek. Now, during high tides, water from the San Diego Bay passes through a culvert beneath Interstate 5 and flows upstream into Paradise Creek. This area is also part of the Paradise Creek watershed, which receives most of its rainfall between October and January. Now, during the months of December and January, there's the overlapping in which there are these huge king tides and there's significant stormwater runoff, which leads the creek to be overfull, so the water ends up overflowing into the streets and floods nearby businesses. Now I'm going to show you what I discussed in the video. So as you'll see in a second, the tide comes in from the Sweetwater River and flows through the community and then drains back to the bottom. The tide is going to come in again, this time with the peak storm happening, following the same motion, bottom to top, but the flooding has a higher reach, as you can see. The flooding begins on 18th Street first and drains out. Now, Julia will talk about the area's surrounding community.
Thanks, Michelle. So to better understand the surrounding population that is affected by the flooding, we utilize the EJ Screen tool. EJ Screen is a mapping tool developed by the EPA to aid agencies in ensuring public health and environment in surrounding communities. By doing this, we were able to assess their socioeconomic status, to find other communities in similar financial situations, and get ideas on how they solved similar flooding issues. We found that in the state of California, this community is in the 81st percentile for low income and in the 90th percentile for being linguistically isolated. That being said, this community experiences more obstacles when they run into setbacks such as unexpected flooding expenses and trying to communicate with their local government. Our client wants to improve the economic condition of the impacted area by resolving the flooding issue. The environmental justice aspect of this project is part of the reason we were so excited to take it on. So how did we get this project? Our project manager, Eric, reached out to the acting city engineer for National City, Roberto Llano, and found out that the flooding issue happening in the Paradise Creek area has been bothering him for a while, but National City did not have the funds to explore designs to solve it. He gave us some ideas on implementing different designs on the Interstate 5 culvert, specifically a flap gate. Roberto requested that we avoid designs that rely on pumps, as they are vulnerable to loss of power and mechanical degradation and in a marine environment. Now Eric will tell you more about our modeling approach.
So when debating how to determine which alternatives would actually be effective, we decided to model them all in HEC-RAS. We chose HEC-RAS because it's the industry standard for projects like this, and we believed it would just have the best tools for the job. So to do this, we had to begin all the way at step 0 and build our model from the ground up, beginning with a hydrology analysis. So we utilized the San Diego County Hydrology Manual to design 2-year, 10-year, and 100-year storms. We use the NRCS method because our watershed is significantly larger than 1 acre, and that's what the manual calls for with a watershed of that size. We followed the step-by-step guidance in the manual and developed 24-hour nested design storms with their peak at 2/3 of the storm duration. This puts the peak runoff at hour 16 of our simulation, which will be important later when we talk about the stormwater and runoff and tidal intrusion interaction. So once we had these nested storm patterns or hyetographs, we input that data into HMS, and that gave us the lovely flow hydrograph that you see here on the left. It also gave us the total SDV for each storm, which you can see on the bottom right. So once we had the basic hydrologic information, we moved to HEC-RAS and used that information to develop our unsteady flow model. We set the upstream boundary condition as the flow hydrograph that we had developed previously. This flow hydrograph is applied at the most upstream cross section. That provides for a fairly conservative model because rather than all of this runoff being applied over the entire area and then making its way into the channel at various points, all of it is applied at one point, and so the upper reaches of the stream experience more stress than they might in the real world. For the downstream boundary condition, we had to somehow simulate the mixed effects of stormwater runoff and tidal intrusion. We decided to do this by implementing a stage hydrograph at the most downstream section. We obtained typical king tide data from NOAA, and we used that to develop the stage hydrograph. You'll notice that both the flow and the stage hydrographs both peak at hour 16 of the simulation. We did this to model the worst case scenario and make our model more conservative. So before modeling the alternatives, so take a step back, we had to develop a base model. This model is basically the real world situation as we observed in our site visits. That includes the riverbanks, flow paths, culverts, road decks, bridges, and et cetera, kind of like along the creek, as well as the general shape of the creek itself and the Manning's values all up and down the creek, all of that. Once the base geometry was complete, we manipulated and changed it in order to model the alternatives. So when modeling the alternatives, our focus was on figuring out how we thought the alternatives would behave and then translating that behavior into the language of HEC-RAS, which Marina will talk more about later in detail. So what's the point of all this? We were trying to measure how effective each alternative would be at reducing flooding. So to do that, we picked one point and labeled it as our observation point. So every time we ran the model, we took a measurement of the depth of flooding at the observation point, and we compared those across all the simulations and all the different geometries. Our observation point was in the middle of 18th Street, right where the creek crosses beneath the road. And we chose this point because anecdotally, this is the first point to flood, and it's the point that floods the worst. So now back to Michelle to tell us a little bit more about the alternatives that we considered.
So our team looked into 4 alternative designs, which were the wetland, the levee, the inflatable dam at the iThe culvert, and the flat gate. And I'll be first discussing the wetland alternative. Now, when choosing our wetland area, we chose an area that was vacant and could be easily converted into this design. As shown in the figure, we found that vacant area measuring to be 4.2 acres between 18th and 22nd Street. Now, this coastal wetland can be built to provide an increase in ecological diversity, provide habitats, and this alternative overall has a low impact. The wetland is also effective in the reduction of rainfall runoff by utilizing the vegetation there to decrease the speed of the flood flow and can provide more water storage, which results in those lower flood heights we want to see. Overall, this can reduce the cost of flood damage. Now I'm going to talk about the design specifications of the wetland. According to the EPA's ratios of acres to storage, this area should approximately be able to hold 4 million gallons of water. The wetland would be connected to the creek by a lateral flow weir. at an elevation of 6 feet above sea level. And in an effort to prevent the wetland from becoming a mosquito infestation, we followed that 72-hour drainage requirement. And to be able to drain in that amount of time, we added those two 6-inch precast concrete pipes. Both pipes would be located at the downstream end of the wetland area and would provide drainage of the wetland between those high tides or huge storm events. Now Marina will be talking about some of the complications we found with the wetland design.
So when modeling and evaluating this alternative, we ran into a variety of concerns and complications. The first being that this land is currently zoned as MXC-2 Major Mixed-Use Corridor. This means that the city receives both property and sales tax revenue from this type of land and could possibly see a significant loss of it by rezoning it. In addition, this area has a high elevation, making it expensive to excavate and ideal for constructing businesses or homes since it's the last area to flood along the creek. Continuing on with the wetland evaluation, when we modeled the 2, 10, and 100-year storms, we saw altered flood patterns. Since the wetland storage area was only capable of holding about a quarter of the total 2-year storm, it became apparent that this would be the limiting factor. When observing the 2-year storm with the wetland storage area, the model showed that the remaining 1.5 million cubic feet of flooding would just be diverted upstream. Although the flooding upstream at the point of interest was the shallowest of all the simulations that we ran, it only redistributed the flooding rather than solving our issue. The 10-year storm model showed a 3% flood increase, and furthermore, the 100-year storm resulted in an 11% increase in water depth at the point of interest. Our next alternative that we modeled and analyzed was the installation of a levee and/or a flood wall. We analyzed the installation of a levee located along both the north and south ends of 18th Street. When running our HEC-RAS model, we discovered that the flooding was shifted from its original location to upstream, just as the previous alternative. Overall, this proved to be an ineffective solution. Based off of our model, it was found that the height of the levee needed to be at least 15 feet in order to be effective. And now you're able to see our model in action. Shown on this slide are the base model that Michelle previously showed being compared with our levee alternative modeled during a 2-year storm. As the video continues, you can see that around the 14th hour, the flooding shifts heavily upstream and floods our area of interest along with its surroundings. Peak flooding occurs during the 16th hour, as Eric previously mentioned, and the water recedes back into the downstream area. Here, these images make it very clear as to where we proposed the installation of the levee. On the left-hand side in the red circle, you can see a lot of flooding. On the right-hand side, you can see in the same area, there's less flooding, but it's shifted upstream into that area, the circle on the right-hand side. The next alternative that we analyzed was the installation of an inflatable dam or a floodgate at the iThe culvert. We first modeled this alternative as a dam with no openings, then as a sluice gate with time series opening, and then finally as a dam. Due to the inflatable dam and floodgate both acting as a barrier, preventing the tide from coming in but the precipitation from draining downstream, we used the same HEC-RAS geometry to model both of these. This alternative resulted in a whopping 77% increase of flooding at our point of interest when modeled just a 2-year storm.
So after spending 4 months modeling and evaluating the previous alternatives, we realized none of them worked. So now what do? We decided to see what would happen if instead of having the inflatable dam at the Interstate 5 culvert, we moved it downstream near an existing pedestrian bridge. We found that by doing this, it prevents tidal intrusion earlier on and allows the existing wetland to be used as a stormwater storage area. When the inflatable dam was modeled at the downstream location, we saw a 24% flood reduction in the 100-year storm.
Here we can see the wetland on the left and the Sweetwater River on the right. When the tide is predicted to rise, the dam will be inflated. When the tide recedes, the dam will be deflated, allowing the water from the creek to drain out and eventually letting conditions return back to normal. As detailed on this slide, when running our analyses for the 100-year storm, each alternative resulted in an increase of flooding except for the downstream dam alternative. Fortunately, when we ran a full analysis, it resulted in a 24% decrease in flooding.
Here's our cost estimate table calculated in 2020 US dollars, including primary cost, maintenance, and a 10% contingency. When estimating costs for all alternatives, we assumed each would have a 30-year lifespan. The bladder of the inflatable dam only has a 15-year lifespan, so we included 2 bladders in this estimate. As you can see, the inflatable dam is by far the most affordable alternative.
So as you may have guessed, our selected alternative is the downstream dam. So on this next slide, on the bottom right, you can see the aerial view of our proposed dam. It's located at the mouth of Paradise Creek, and as you can see, there's an existing pedestrian bridge and bike path here. We don't anticipate the dam installation interfering with this bridge, as the dam will be located further into the mouth of the creek than the bridge is. On the left, we have the dimensions of our proposed dam. The dam is about 34 feet across the bottom and 12 feet high. The foundation is designed using 1,800 cubic feet of reinforced concrete, which provides stability, but also counteracts the buoyancy of the dam. We chose a 12-foot dam height because the king tides can reach 9 feet, and to hold the entire 100-year SDV, the wetland area would fill up to 8.2 feet. So that 12-foot dam provides a 25% safety factor. Additionally, in the time of climate change and sea level rise, this 25% safety factor ensures that we'll be able to get that full 15-year lifespan out of the dam. So here we have a picture of an inflatable dam in action for those of you who may not have seen this before. These dams are air inflated and they're attached to concrete foundations. Our dam will be held in place by 20 clamp plates. These clamp plates are basically attached to bolts that are cast into the concrete, and then there's another plate that goes inside of the dam and basically like screws down and creates an airtight clamp. This allows the city to remove just the bladder when that 15-year lifespan is up without having to remove or replace the entire foundation. So finally, we've covered the upstream impacts on Paradise Creek, which were positive, but we haven't talked about the upstream impacts on the Sweetwater River, right? Which is the other body of water that's affected by this dam. Fortunately, we don't anticipate there being any negative upstream effects on the Sweetwater River, as we are only preventing tidal water from entering Paradise Creek, and this will have no effect on the Sweetwater River. So I'll turn it over to Michelle for the conclusion.
So ultimately, choosing the inflatable dam is the best option since it was the most effective for the flooding. Additionally, it had by far the lowest cost, as Julia pointed out. The alternative is also considered a low-impact design that takes advantage of that natural storage area and is not invasive geologically and ecologically while making use of on-site features. This overall makes it easier to permit. And now back to Eric for some final words.
So thank you so much for watching our presentation. We'd also like to give a special shout out to Dr. Christy Dykstra at San Diego State University. She's our mentor and got us involved with WEF. And we'd also like to give out a shout out to those engineers who helped us at various stages of this process, and to WEF for putting on such an awesome competition. We're stoked to have been involved. Thank you.